Hello everyone. It is a great pleasure to present our recent work on optimizing the DC equivalent series resistance in compact PCB-based resonant couplers for capacitive power transfer systems. This slide outlines the structure of the presentation. I will begin by introducing the background and motivation of our research. Next, I will discuss the analysis of the capacitive power transfer system under investigation. In the third part, I will present the proposed two-stage optimization strategy, along with its technical details. Following that, I will share the experimental results obtained using the optimized PCB-based couplers we have fabricated. Finally, I will conclude the presentation with a summary of key findings. This is the introduction part. Wireless power transfer systems can be categorized based on their physical field implementations into inductive power transfer, IPT, and capacitive power transfer, CPT. In general, IPT offers superior power handling capability and robustness against misalignment, while CPT provides advantages in thermal management, electrical magnetic interference, and power density. IPT systems have been widely adopted in consumer electronics and biomedical devices, but CPT systems are gaining increasing attention in electric vehicles and robotic applications. This is a typical schematic diagram of a CPT system, which consists of a capacitive coupler along with compensation networks to transfer power from the transmitter to the receiver through electric fields. The compensation networks are usually inductive, forming LC resonators that significantly enhance power transfer capability. The figures here illustrate conventional CPT systems using CPT couplers and compensation inductors. Since both the couplers and compensators are handmade, they typically exhibit around 10% perimeter deviation. This can affect the efficiency and power quality of the CPT system, especially under high-frequency operation. As power electronic systems continue to advance toward higher power levels and higher operating frequencies, conventional CPT designs need to be upgraded with standardized design methodologies. PCB-based CPT couplers offer a promising solution. They feature integrated inductors, a more compact structure, and greater ease of optimization. Furthermore, PCB-based couplers can be manufactured in large quantities with consistent and precise perimeters, typically with only about 2% deviation. They also offer flexibility in switching between CPT and IPT modes, depending on application needs. This slide presents the development roadmap of PCB-based couplers. These couplers were originally designed for IPT systems operating at megahertz frequencies, where conventional lead wires tend to suffer from poor quality factors within that frequency range. In the early 2000s, single-layer PCB-based couplers were introduced as planar transformers. Each transmitter and receiver consisted of a single-layer PCB trace, requiring external compensation circuit to function effectively. By the 2010, double-layer PCB-based couplers emerged, utilizing the straight capacitance between the two layers to eliminate the need for external compensators. In 2020, multi-layer PCB-based couplers were developed to allow greater design flexibility and to support higher output power and improved efficiency. In 2023, a sandwich structure coupler was introduced, where the FR4 dielectric material was replaced with air between the copper traces on both the transmitter and the receiver sides. This design significantly reduced power losses and improved performance. Further optimization of this sandwich structure was carried out in 2024. Also, in 2023, this sandwich structure PCB-based coupler was successfully validated for CPT applications. The role of components were reversed. The compensating capacitors and coupled inductors in IPT systems were repurposed as coupled capacitors and compensating inductors for CPT systems. However, optimization of such CPT couplers have not yet been explored in existing literature, and this work aims to fill that gap by proposing a two-stage optimization method to reduce the equivalent series resistance and improve the system performance. PCB-based couplers designed for the CPT system consists of an outer coupler and an inner coupler on both the transmitter and receiver sides. This configuration offers high compactness and allows for the optimization of multiple design parameters. In this work, 6 key parameters are optimized to minimize the equivalent series resistance. A common approach to optimization is to minimize the equivalent resistance derived from the equivalent circuit. But this method is limited in accuracy, whether using a simplified first order or complicated high order model. This limitation arises because mutual couplings and the parasitic elements are difficult to be fully captured and represent in circuit-based models. As an alternative, optimization can be performed using the finite element model. This approach is typically implemented in simulation platforms such as ANSYS, while FEM-based optimization offers greater accuracy by capturing the electromagnetic interactions in detail. It is computationally intensive and time-consuming. Additionally, the optimization process often requires complex search algorithms to minimize the objective function effectively. The motivation behind this work is to strike a balance between the accuracy and the computational efficiency in optimizing PCB-based CPT couplers. The main contribution is the development of a new optimization strategy aimed at minimizing power losses in these couplers in this paper. Compared to methods based on the equivalent circuit models, the proposed approach offers higher accuracy. Compared to the purely FEM-based methods, it significantly reduces computational time and complexity. Then I will analyze the investigated CPT system. This is the equivalent circuit diagram of the system under investigation. It includes a DC power supply, a full bridge inverter, a SS compensator transformer, a PCB-based CPT coupler, a dial bridge rectifier, and a load. It is important to note that V1 is a square wave AC voltage, which contains significant high-order harmonics. And the CPT coupler have multiple resonant frequencies due to parasitic elements. So to suppress these unwanted high-frequency components from propagating to the receiver side, this SS compensated transformer is employed in the design. Unlike conventional CPT systems, which use separate couplers on 2 plates, this design integrates both an outer and an inner coupler in one single plate. This configuration improves compactness and reduces losses. But it also introduces complex cross-couplings among the inductive components, which makes accurate analysis using conventional circuit theory highly challenging. This diagram shows the fundamental equivalent circuit. Based on the frequency domain simulation analysis here, you can see that the fundamental series resonant frequency is 3.62 MHz, which allows effective power transfer to the receiver at this frequency. The first parallel resonant frequency appears at 5.91 MHz, which blocks power transfer at that frequency due to the resonant behavior of the CPT coupler. Similarly, the second parallel resonant frequency is located at 7.9 MHz, and also inhibits power transfer. The inclusion of the SS compensated transformer is crucial for filtering out the second series resonant frequency at 7.34 MHz. Without this filter, power at this frequency would also propagate through the CPT coupler, potentially affecting system performance and power quality. These two equations illustrate the fundamental design principles governing the resonant frequencies of the CPT coupler and the SS compensated transformer. The main objective of this work is to enhance overall system efficiency, as shown in this equation. Improving efficiency can be achieved by minimizing the equivalent series resistance, which directly impacts power losses in the system. Based on the aforementioned design principles, I further illustrate the proposed two-stage optimization strategy for the PCB-based CPT couplers. Here are the fixed parameters for the coils. The diameters of the PCB, outer coupler, and inner coupler are predetermined based on the application requirements. The thickness of the copper traces is limited by manufacturing constraints from the supplier. PTFE is selected as the substrate material considering both cost effectiveness and the low dielectric loss. These 6 parameters are selected for optimization as they significantly influence the equivalent series resistance and the quality factor of the systems. These parameters include the total number of terms for both the outer and inner couplers, the outermost trace-wise, the spacing between adjacent terms, and the term-to-term ratio for both the outer and inner coupler. This figure illustrates the overall structure of the proposed optimization algorithm. The 6 design parameters, along with their respective boundaries, are first input into a Latin hypercube sampling process. This sampling method selects a representative subset of parameter combinations for evaluation, rather than exhaustively testing all possible combinations. Further details on Latin hypercube sampling will be discussed on the next slide. The sampled data points are initially filtered based on geometric constraints. Only those that met the defined boundaries are passed to a high-dimensional knowledge base. At the same time, each valid parameter set is simulated using FEM to extract the corresponding equivalent series resistances and the resonant frequencies. These outputs are then evaluated through the objective function, and the resulting objective values are recorded in the knowledge base. To visualize and analyze the high-dimensional data, the TSNE algorithm is used to reduce the dimension from 6 to 2. The reduced dataset is then processed by a ranking module, which selects the top 20 out of the initial 200 samples for further exploration. The remaining 180 samples are set aside. The top 20 selected samples are expanded into 200 new candidates using a dictionary searching algorithm, which will be explained later. These new samples are also evaluated using the same objective function, and their results are merged with the initial dataset to update the knowledge base. Finally, the optimal set of design parameters is selected from this enriched and refined dataset. The core idea behind the Latin hypercube sampling is to efficiently select a reduced number of sample points that are evenly distributed across the parameter space, rather than exhaustively evaluating all possible combinations as done in full factorial methods. As the number of design parameters increases, the computational advantage of Latin hypercube sampling becomes more significant. The Latin hypercube sampling process begins with stratification, where the range of each parameter is divided into equal intervals. A sample is then randomly selected from each interval along each axis independently. Finally, the sampled values cross dimensions are randomly paired to generate well-distributed sample sets. To visualize the six-dimensional perimeter space, the PSNE algorithm is applied to reduce the dimensionality to 2. This allows for clear visualization of the knowledge base. 200 generated datasets in the knowledge base are then evaluated using the objective function to guide further optimization. The objective function used in this study consists of two components. The first is a resistive term, which accounts for the sum of the ESRs of both the outer and the inner couplers. The second is a frequency term, which represents the difference in resonant frequencies between the two couplers. Two weighting factors, alpha 1 and alpha 2, are applied to balance the influence of these two terms. Since the primary goal of this work is to minimize the DC ESRs, the resistive term is given greater importance by setting alpha 1 to 5, while alpha 2 is set to 1 in this work. After computing the objective function for each dataset, the 200 samples can then be ranked accordingly as illustrated in this table. We selected the top 20 samples for further processing based on their objective function values, while the remaining 180 samples were excluded from the next stage of the optimization. The top selected 20 samples are used as reference points, as shown in this figure. For each reference point, 20 new candidate samples are generated. The distance between each candidate and its corresponding reference point is then calculated. If all newly generated candidates fall outside a predefined threshold region, illustrated by the boundary in this diagram, the entire set of 20 candidates is discarded. If at least one candidate is located within the threshold region, the reciprocals of their distance to the reference points are calculated and used to determine selection probabilities through a roulette wheel method. This probabilistic approach helps account for any potentially missed optimal samples in the initial Latin hypercube sampling and improves the chances of identifying better performing solutions. The roulette wheel selects one candidate from each group of 20, with higher probabilities assigned to those closer to the reference points. This process is applied to all 20 reference points, resulting in the generation of 200 new candidate samples. These newly generated samples are combined with the 180 previous set-aside samples and the 20 reference points to form an updated knowledge base. This expanded dataset is then re-evaluated using the objective function. Based on the recalculated objective values, all samples are re-ranked and the new optimal solution is identified. This optimal design is subsequently used for the fabrication of practical CPT couplers. Here are the experimental verification results. This diagram highlights the differences between the optimized CPT coupler and the conventional design. As shown, the outer coupler in the optimized version has a different number of terms, and the trace-wise increase progressively from the outer edge to the inner side. In contrast, the conventional design features traces that become narrower toward the center. A detailed perimeter comparison is presented in this table, showing that all design perimeters differ between the two versions. The optimization results in a reduction of the objective function value by approximately 39.6%, indicated a substantial performance improvement. We measured the impedance characteristics of the optimized PCB-based coupler using an impedance analyzer. The results show noticeable shifts in the resonant frequency of both the outer and inner coupler. In terms of DC resistance, the outer coupler experienced a significant reduction of approximately 67.9%, dropping from 2.18 ohms to 0.7 ohms. The inner coupler's DC resistance was reduced by about 23.3%, from 1.87 ohms to 1.36 ohms. Overall, the total DC resistance decreased by approximately 49.1%, demonstrating the effectiveness of the optimization. Here are the conclusions. From this study, we have identified several key design principles to reduce ESRs. This included decreasing the spacing between the adjacent terms, increasing the term-to-term ratio of both inner and outer couplers to values greater than 1, widening the outermost trace-wise, and reducing the number of terms in both couplers. However, we observed inherent trade-offs among these parameters, making manual tuning challenging. Therefore, optimization algorithms are essential to balance these competing factors effectively. In this work, we fabricated optimized PCB-based CPT couplers that achieved a 27.3% reduction in outer coupler resistance, a 67.9% reduction in inner coupler resistance, and a 49.1% decrease in overall resistance compared to the conventional design. These improvements contribute significantly to enhancing the efficiency of PCB-based CPT systems. That's the end of the presentation. Thank you for your attention.